Good morning, class. We are looking at section 5.4, the substitution rule. And the session is being recorded. We went over the first half of that. We have integration formulas we need to be comfortable with. The substitution method simply is the reverse process of the chain rule. Therefore, in order to use this method, the tip is look for a function u equals g of x and its derivative. For example, in this case, which contains polynomials, we look for the more complicated one as the function of interest u, in this case x squared plus 5. The derivative of that is 2x, therefore du becomes 2x dx. As long as we can find these two, practically we are done. By the substitution method, we end up with the simple case of a power rule, and we replace the u with x squared plus 5, and that's our final step. Same situation here. We are dealing with polynomials. The more complicated one, x cubed plus 1, is a choice of u. The derivative is 3x squared. Therefore, 3x squared dx is du. So we make the transformation, becomes a power rule. We reverse the substitution by using the original variable. We're done. Although we can distribute, there is no need for a substitution. For the sake of the section, we are going by substitution. The more complicated one, x squared plus 3x plus 5 is a choice of u. 2x plus 3 is the derivative, so 2x plus 3 dx is du. And number 9 remains as a multiplier. Whether you leave it inside the integration sign or outside makes no difference. Fractional expression, rational expression, they work in the same way, meaning number one, we try to simplify if we can. If we cannot, normally the denominator is a choice of u. In this case, as you can see, the derivative of the bottom is the top. So if you choose u to be 5 plus e to the power of t, the derivative is e to the power of t, and du becomes e to the power of t dt, resulting in a format which gives us a natural log. Same thing here. We want to try to differentiate, to simplify. We cannot. If you choose the denominator to represent u, its derivative is 2x plus 2, and the numerator is almost that. What is missing? A factor of 2. Anytime a number is missing, it is not a problem. We can multiply and divide by it. I put them in different colors just to make sure everybody can clearly see. We are multiplying by 2, and then we are multiplying by its reciprocal, so their product is 1. Again, this portion, natural log, we finish the job. Same page. I'm using the reciprocal of part A, so you can see that there is no need to do the substitution. So you want to distinguish between the two, because now we can make up two fractions and avoid using substitution. Anytime we have exponential functions, normally the exponent is a choice of u. When u is x to the power of 5, the derivative is 5x to the power of 4, and du becomes the product of 5x to the power of 4 dx. So this transforms to the integral of e to the power of u du, which is e to the power of u plus a constant. Replace it, and you're done. Same thing happens here. The exponent is a choice of u. When you take the derivative of this, becomes 5x to the power of 4. So du is 5x to the power of 4 dx, and number 5 is missing. You can multiply and divide by it. And finish the job. I chose this one to show you the method that the text does. If you choose 3x plus 7 to be u, then du is 3 times dx. And the method that I went over, number 3 is missing, so it's not a big deal. Put number 3, that means multiply by it, and undo it by multiplication by its derivative. In other words, I would do the following. I would put number 3 in here and 1/3 out. Their product is 1, and that's a faster way of approaching it. However, this is simple enough. We can follow the method that the text does. They do solve for dx, and they go through the process. The more complicated du, the more difficult this method. They finish the job that way. They ultimately end up with the same thing that we wanted to get in the first place, and they come up with the answer. U to the power of 1/2. We've done it many times, and that's the final answer. If ln x is involved, most likely ln x is a choice of u. So if you choose ln x to be u, du becomes 1/x dx. If you can see that, fine. If not, rewrite it such that you can see different components as follows. So when you see it in this format, you can see this is u squared du. You use the power rule, you finish the job. Same thing happens in part B. You rewrite it so you can see various components. And now 1/u itself becomes a natural log, and replace the u. When you're dealing with sinusoidal functions, if the argument, in this case x squared, is being raised to a power, that is the choice of u. When you do that, you notice the derivative of x squared is 2x dx. Number 2 is missing. You can put the 2 in and undo it by putting 1/2 out, and the rest is history. Needless to say, you can differentiate the final result, and that should give you this one without the dx. Now, in part B, sine is being raised to the power. It doesn't matter if it's sine squared or sine to the power of 10 or sine to the power of 15. Then u equals sine x. The derivative is cosine. So du is cosine x dx. By the way, again, even if cosine is being raised to a power, then you choose cosine to be the u. The derivative is negative sine x, and you want to be careful with the positive negative sign. Having said that, we rewrite this as the integral of u squared du, which becomes a power rule again. Replace the u, and the final answer, you can always differentiate to see if you're correct as far as checking your work is concerned. The last thing we looked at was a definite integral. Definite integral results in a number. So we are looking to find a number. So there are two methods. We can always go back to the original variable x. So this is a simple case. We've seen a similar case like this. We let x squared minus 1 to be u, and du becomes 2x dx. Now, as far as the u is concerned, again, we don't know the limits. We don't worry about that, because we're going to go back to the original variable, namely x. We plug in 2, we plug in 1, we do the math, we are done. So you can always go back to your original variable x, original limits, in this case 1 and 2. Or So returning to original variable, or keep the track by plugging in 1 into the u, giving you 0. So the lower limit 1 results in lower limit 0. The upper limit 2 gives you 2 squared minus 1 or 3. So the new upper limit is 3. So you can keep track of that. And therefore, when you are here, you write it as 1/4 u to the power of 4. From 0 to 3. Either way is fine. And the theorem is that the integral of a to b f of g of x g prime of x dx, then when you go with the u substitution, a changes to g of a and b changes to g of b. Let's look at a new example. We notice that we can rewrite this, of course, as 25 minus x squared to the power of 1/2. That is the choice of u, 25 minus x squared. The u becomes negative 2x dx. And that means negative 2 is the missing number, if you will. So negative 2 is not there. We can put a negative 2 and undo it by putting its reciprocal negative 1/2 out. Therefore, we have a u substitution as follows. Notice I'm not putting the limits for the u yet, because again, I want to make a point. We can always go back to the original limits and original variable and original limits. We come back to the u in a moment. This one, we've done it many times. This changes to u to the power of 1/2. And this part, 1/1/2 plus 1 u to the power of 1/2 plus 1. Don't forget, we have a negative 1/2 in front. 1/2 plus 1 is 3/2. 1/3/2 is 2/3. These two and these two cancel each other. We get negative 1/3 u to the power of 3/2. Again, we are not putting the limits yet. Let's go back to the original variable and original limits. So we can evaluate it this way, and that's fine. However, what if we want to go and use the new limits? So let's plug in number 3. We get 25 minus 3 squared, which is 9. So the new lower limit is 25 minus 9 equals 60. Let's put in the upper limit 4 into the u. My 25 minus 4 squared, which is 25 minus 16 equals 9. So the new limits are 16 and 9. We're going to evaluate those by plugging in. So we get negative 1/3, 9 to the power of 3/2 minus 16 to the power of 3/2. So what is 9 to the power of 3/2? This is square root of 9 cubed, which is 27, minus square root of 16, which is 4, cubed, which is 64. 27 minus 64 gives us negative 37 times negative 1/3 gives us positive 37/3 as the final answer. We want to evaluate the integral. Again, going through the process, let's go with the u substitution. If we let u be 2x cubed minus 8, its derivative is 6x squared, so du becomes 6x squared dx. What is missing? Number 6. So we're going to put number 6 here, and its reciprocal out. We rewrite it. And again, we don't have the limits. We want to figure out the limits. So we're going to put 0. That gives us clearly -8, right? We plug in 2. That gives us 2 times 2 cubed -8. 2 cubed is 8 times 2, 16 minus 8 is 8. So we have the new limits. This part is 1/4 u to the power of 4. With 1/6, their product is 1/24. So we're going to put either the new variable u with the new limits or the old variable x with the old limits. Either way results in the same thing. However, I believe the new one is easier to evaluate. Take a look. This is equal to 1/24, 8 to the power of 4 minus -8 to the power of 4. Because the exponent is even, 8 to the power of 4 and -8 to the power of 4 are the same. They are both positive. They cancel each other and they give us 0. Again, pay attention to the fact that the exponent is an even exponent. Therefore, 8 to the power of 4 is the same as -8 to the power of 4. The rate of growth of a fish population is given as such. G of t is 30,000 e to the power of -0.6 t over 1 plus 5 e to the power of -0.6 t quantity squared. This was modeled by the equation where t is measured in years since what year? 2000. Lowercase g in kilograms per year. So take a look at two things that are important to remember. This is the rate of growth. That means this is a derivative function in essence. And look at the units, kilograms per year. If the biomass was 40,000 to begin with in the year 2000, so we start with the initial value of 40,000. What is the predicted biomass for the year 2020? So you are looking at the same concept that we looked at before, meaning we are dealing with a definite integral here, accumulated change or net change theorem. So the amount of increase takes the place of the integration. So G of t represents the growth rate, the accumulated change, therefore is the amount of increase over the course of 20 years by using the integration formulas as follows. From 0 to 20, the integral of 0 to 20, G of t dt. We've seen the same type of problem, but we didn't have to do it by substitution before. Now, again, you want to simplify if you can. This cannot be simplified. If you choose the denominator to be the choice of you, I hope you notice that the derivative of this is 5 times -0.6, which is -0.3 e to the power of -0.6 t. So du becomes what I mentioned times dt. So take a look at u. This is u. The derivative of that is 5 times -0.6, which is -3 e to the power of -0.6 t. That's du dt. So du is the same thing times dt. Now, what happens is The numerator is 30,000. One easy way to look at this, you would need -3 at top, but you have 30,000. I hope you see that -3 times -10,000 becomes 30,000. So 30,000 is the product of this number, -3 and something else. If it's not divisible by one easy way, you can take the 30,000 out and put a -3 and divide by. Either way is fine as long as you recognize this is really just a number that we can create that by multiplying and dividing by. So again, if you put -3 up here, 30,000 divided by -3 gives you -10,000. So what we are looking at is -10,000 du over u and new limits. Now, let's discuss the differentiation and let's discuss the limits. The differentiation, we've seen it many times. This is 1 over u squared class. So let's just quickly do that, although we've done it many times. This is 1 over u squared. Let's just go to u to the power of -2 du, right? Therefore, it's 1 over -2 plus 1 u to the power of -2 plus 1. And this is the same as negative u to the power of -1, or simply put, -1 over u. You can write this even as -1 over u. Either way is fine. So that's as far as integration is concerned. What about the limits? Let's plug in 0 here. If you plug in 0 class, you get 1 plus 5 times e to the power of 0, which is 6. If you plug in 20, we get 1 plus 5 e to the power of -0.6 times 20. -0.6 times 20 is -12. So let's quickly see how we get that one more time. If you plug in 0 into the u, this becomes 5 and 1 is 6. If you plug in 20, okay, 20 times -0.6 is -12. That's how you arrive at it. So with that being the case, we can say, and don't forget that there's a -10,000 in front. -10,000 and negative becomes +10,000 divided by u, or +10,000 times 1 over u. You can think of this as, let me write it in that format also. This part is the same as saying 10,000 times 1 over u. And now 1 over the upper limit, 1 over 1.00031. When you do that division, for all practical purposes, becomes 1 minus 1 over 6. So take a look. This is what you get. And it can be approximated by about 8,333 kilograms. Now, I need to erase this. Let me do that. So we had 40,000 to begin with. I hope everybody remembers that. We're going to add that to what we got, and this is the answer. And if you recall, we also did one of those questions with a different method, namely going back to the original function. When we look at the given, this is the growth rate. This is lowercase g of t. So what is capital G of t? Remember what we got here. So capital G of t is 10,000 over u plus a constant. 10,000 over 1 plus 5 e to the power of minus 0.60 plus a constant where the initial value is 40,000. That means g of 0 is 40,000. Now, you can go through the process and find the constant. It ends up being 38,333. I'm going to leave it for you to show that. And what we want now in the year 2020, we want capital G of 20. So replace in this equation t with number 20, and that gives you the same answer. These are two different methods, applications of a substitution method. Now, how about this page? We are looking at similar questions. It's worth noting that. The very first thing is simplification of a rational expression if you can. And when it cannot be done, then you move on to the next step. So if you look at part A and B, ultimately they work out the same. You let u be the denominator, 1 plus x squared. Du becomes 2x dx. And the first one changes to the following integral. It's a familiar one, natural log. Replace the u, we're done. Now, notice I didn't put an absolute value because 1 plus x squared is always positive. Otherwise, we must. Now, we use the same substitution for part B, but I want you to notice the difference. Now, we are going to bring the u up. Therefore, we notice that it's completely different when you compare it to A. And now we are using the power rule. U to the power of -2, we've seen it many times, but let's quickly look at this again. It's 1 over -2 plus 1, u to the power of -2 plus 1, which is minus u to the power of -1 or minus 1 to the power of u, this part only, okay? So -1 and over u, u is 1 plus x squared and a constant, and we are done. As for part C, with enough practice, you may see the answer just by looking at it. But for now, by u substitution, let u be the denominator and the u becomes dx. So this is the integral of du over u. Again, the good old natural log. Replace the u, going back to the original variable, and we're done. Notice we need the absolute value sign because x plus 3 can be positive or negative.